How is ours?
He's not gonna know the future.
How's ours?
She was like, oh, can you put heat?
Does everything like
Bro, it was so funny. She was like,
like with libraries or
Okay, the fact that Phil's got second place,
It's big enough,
person
you know?
place 14th is actually.
Yeah.
You don't deserve second at
Every
that.
possible way.
yeah, how did you so it's everybody
Every other way cancels out.
Okay, are we going, Danny? All right. So we're going to make this mathematically simple. Okay, in reality, these numbers are not nearly work out this nicely because charges are really, really small numbers like 10 to the negative 9th and all this good stuff. But I just want to set this up as easy numbers so you can see the pattern. So at any point, the kinetic energy plus the value of some potential energy is going to add up to a constant. And I just picked a number to make it easy. I want to say, okay, the constant's going to be 20. Okay? Boom, that's what I got. It's just 20. So I'm going to have a positive charge and I'm going to have a negative charge. So do they want to attract each other or do they want to repel? They're going to attract. Now, because of the fact that I have two oppositely charged particles in here, that means this number up here is going to be a negative number. Okay? Don't get hung up on like that negative sign out front, because with positive and negative charges, it gets a little bit wonky. It's just going to be a negative value because it's going to make the math work out. So this value up here, I'm just going to let it be negative 12 Newton meters squared. So situation number one, these charged particles are 6 meters apart. Okay, so 6 meters apart is from that wall about to my desk. Okay, it's a pretty fair distance. Then I'm going to bring him to 3 meters away, and then I'm going to bring him to 2 meters away. Okay, so we can go through and we can calculate this value of what OOE is going to be. So we can sit here and go, okay, we're going to calculate OOE at these different distances, 2, 3, and 6 meters. So OOE at 2 meters, OOE at 3 meters, OOE at 6 meters. So at 2 meters, OOE has a value of negative 6 joules. At 3 meters, OOE has a value of negative 4 joules. And at 6 meters, OOE has a value of negative 2 joules. Okay, cool, right? So as the distance gets smaller, what happens to the, and don't get hung up on, this is not a math class, like negative 6 is less than negative 2 or whatever. Okay, this is not a math class on the number line, all right? So as the distance gets bigger, when you go from 2 to 3 to 6, and you push this negatively charged particle away from that proton, what happens to the value of OOE? Decreases. So if you were to draw a graph, and the graph itself gets a little bit weird. So if you were to look at distance, and there's 2 meters, 4, 6, and then you got negative 6, negative 4, negative 2, these are joules. So you'd have a point out here at 6 meters and negative 2 joules. You'd have a point of 3 meters and negative 4 joules. And you'd have a distance of 2 meters and negative 6. So this graph is going to go something like this, okay? So as the distance gets smaller and smaller and smaller, what's going to happen to the value of OOE? It's going to get bigger and bigger and bigger, but it's going to be a negative value, okay? So as you take those oppositely charged particles, Okay, and this is gonna be important because of oppositely charged particles. And basically, what you're trying to do is that you've got to keep them from going towards each other because they're oppositely charged, okay? So now we're gonna look at the conservation of energy, where OOE plus kinetic energy has to equal 20. So we're gonna look at 2 meters, 3 meters, and 6 meters. So at 2 meters, my OOE value was -6. At 3 meters, that was -4, and 6 meters, that was -2. So in this situation, my kinetic energy would be 26 joules. Now, why can my kinetic energy never be a negative value?
Balance out the negative values.
Well, how do you calculate kinetic energy? 1/2 mv squared. So even if you have negative velocity, you're still going to square it. Okay? So your kinetic energy can never be a negative value because that says to add up to 20. So then I'm going to have 20 plus 24 joules, and then plus 22 joules to get to 20. Now, if you were to draw a graph and put distance and kinetic energy on that graph, and you had 2, 4, 6, okay, what's that graph going to look like? Well, at 6 meters, you're at 22. At 3 meters, you're at 24. And at 2 meters, you're at 26. So that graph's going to go something like this. Now, here's where it all comes together. So stay with me here. So imagine that you've got this proton and you have an anchor. So I have an anchored proton, and I've got this electron that I've done work. We'll talk about work later on. And I've pushed that electron way out here. I've separated these two. So as soon as I let go of it, what's the electron going to do? It's going to start moving towards the proton. So as it moves towards the proton, and it gets closer and closer and closer and closer and closer, so you're going from 6, at 6 meters it had 22 joules. At 3 meters it had 24 joules. At 2 meters it had 26 joules. Cool. So as the electron approaches, what happens to its kinetic energy? It goes up. So as it gets closer, and if I decrease that distance, I'm gaining kinetic energy, which means it's doing what? It's going faster and faster and faster. But if I drop that distance from 6 to 3 to 2, what happens to the value of my negative OOE? The magnitude increases. So as I decrease that distance, I'm increasing the magnitude of my negative OOE. Now, this is in sharp contrast to UG being MGH. And if you look at UG being MGH and I just drop this thing, as it falls, what happens to the value of UG in terms of MGH? MGH becomes smaller. Kinetic energy gets bigger. Oh, that makes sense. But if you have oppositely charged particles, as it approaches, it does go faster, but you're increasing the amount of negative OOE. Okay? Now, think back to that field lab that you all did. If I put a positive charge here in the middle, remember the lines of equal voltage? Okay, you hit the little plot point, and you'd have lines that go out like this. Okay, all right, everybody remember that? And that was KQ over R. Anybody remember, as you get further and further and further, what happens to the value of that voltage? Did it get bigger or smaller? Smaller. Okay, so this might be like 20 volts. This might be like 10 volts. That might be like 5 volts. Okay? Now, imagine that I have a positive proton. And visualize this. I'm going to throw that proton towards that other proton. I'm going to throw it this way. As I throw it, and release my hand, what's going to happen to that proton as it approaches the other one? Is it going to speed up or is it going to slow down? It's going to slow down. Now, this is going to look a little bit weird when I initially draw it, but it'll make sense. So we're going to have a positive voltage mountain. Okay? So there was the positive charge. So if you've ever studied geography, you have like contour lines of equal elevation. Okay? All right? And so you've got like a 20 volt line, and then you've got like a 10 volt line, and then you've got like a 5 volt line. Okay? So if I throw that proton and try and throw it up the hill, this works like you're used to thinking of. If I take this and I throw it up, that makes sense to you because you're sitting there going, oh yeah, it's like two positive charges. I roll it up the hill, I'm increasing my amount of OOE because of the fact that it's still KQ1, Q2 over D, but now I have positive charges. So as it gets closer, I'm dividing by a smaller distance, and then I increase my amount of OOE. Oh, cool, that makes sense. But it's like I'm rolling it up the hill. So as I roll it up the hill, OOE as a positive value is going to get smaller. My kinetic energy is going. What's going to happen to the amount of kinetic energy? Yeah, so my OOE, I misspoke. My OOE is going to get bigger. My kinetic energy is going to get smaller. Cool. That fits. That's like a normal situation. Oh, that's normal gravity. That kind of makes sense. But if that had been a negative charge in the middle,
It's going to keep climbing into it.
so then you would have like negative 20 volts, and then you would have negative 10 volts, and you would have negative 5 volts. Now, if I throw a proton towards that negatively charged electron, what's it going to do?
Keep climbing.
It's going to speed up. It's going to go, oh, I like the direction this is going. So in one situation, I let go of that proton, it's going to speed up. The other situation, I let go of that proton, is going to slow down. And it all depends upon if the charges have the same value or if they have opposite charges. But no matter what,
Excuse me.
did you just stop at one sneeze?
No, it was two sneezes. The first
I
one was
just
really
gonna say,
small.
Danny, holy cow, in all the years I've known you, I've never known you to be one sneeze. Okay.
Yeah.
So it's just, wow, that's weird. Okay. So this is where work becomes part of this. So if you look on, Kevin, hand me both of your equations.
Danny, Gilson will hear about this.
All right.
First hole was a warm-up sneeze. What if it's two sneezes.
Okay, thank you. Okay, so let's talk voltage. So for my AP chemistry students, what's the units for voltage? Joules per Coulomb. Cool. So if you look at this in terms of voltage, now, it's one of the very, very few instances that the delta sign is absolutely vital to understanding this. So notice this is a delta V. This is not velocity, this is voltage, okay? Now, there's certain annoying things that happen when you study chemistry. And you would think that they would have this sorted out by now, but they don't. One annoying thing is that we still view electricity as positive charges that are moving, we'll talk more about that later, that has to do with Ben Franklin. That's all on him. But we never changed it. The other thing is that we can't settle on voltage. So sometimes you'll see voltage written as a V, sometimes you'll see it written as a fancy E, which stands for electromotive force, okay? And you would think, by now, can we just not settle on just V for voltage? Do we still have to use two different symbols? Yes, we do, okay? Don't fight it, don't try and change it, you're not gonna win. It's just the way it is. So if you see this fancy E, it means the same thing. So if you look at this in terms of units, UI is going to be measuring what? Joules. Q is going to be joules per coulomb, which is what voltage is measured in. Now, here's the significance of the delta signs. This is not voltage. When you're talking about change in voltage, that's literally what it means. So if I go, like for example, your typical household is at 110, let's say 110 volts, okay? Well, if you boost that up to 120 volts, your delta V is obviously going to be 10. If you went from 10 volts to 20 volts, it's the exact same change. So this is not the actual value of the voltage. It's how much the voltage changes, okay? And that's going to be the fundamental difference. So then that's going to play out with the change in UI. So what that means is that if I don't have a change in voltage, if I have an electron moving, kind of like if you remember back to your days where you studied centripetal motion and life was simple, okay? And we have the rubber stopper going around like this. Once I get it up to speed, is work being done? No. Why?
There's no force being exerted.
There's a force, but what's the direction of the force?
Inward.
Force is inward at a right angle to the velocity vector. So the force is going this way, but there's no displacement in that direction. So there's no work being done. Now, did I do work to get it to move? Absolutely. But as I move this thing around like this, if everything is staying the same, I'm not doing any work. So if you look at a simple idea, it's not nearly this simple, but if you think about it, and you have an electron moving around a proton. And if that electron isn't moving in terms of the voltage around that proton, then without a change in that voltage, there's no change in the UI value between that electron and that proton. So if you change the voltage, then you're going to change the value of UI. So this isn't voltage, okay? This is change in voltage, okay? And that's a huge thing. So the other way that you can see this, and this how this is typically written, is that if you solve this for delta UI, and that's change in voltage times Q. Now, let's talk about this. If you look at this in terms of UI, okay? In a broader idea, what does work always equal?
Force times distance.
Force times distance, it also equals a change in
Energy.
some type of energy. Kinetic energy, potential energy, rotational kinetic energy, something. So if I solve, since I've got this in terms of UI, and I write this and I solve for delta V, and I write that as delta UI over Q, okay, to get my voltage. Well, that got weird. Now an arrowhead appeared. So I can also write that because change in UI is also going to be the amount of work that's done. So I can also write this as work over Q, and then if you wanted to solve for work, you could write that as change in voltage times Q. And here's a broader idea, and it's the same thing. If I don't change the voltage, how much work do I do? None. It's just like if I hold this mass out here, am I exerting a force? Yes, I'm exerting a force because I'm keeping this thing from falling. I'm exerting a force. But like you all said, work also equaled force times the distance. But I'm not moving it in the direction of the force. I'm just holding it out here. Am I exerting a force?
Yes.
Is my arm getting tired?
Yes.
Yes. Am I doing work?
No.
No. If I lift it up, do I do work?
Yes.
Do I change the value of UG?
Yes.
Then when I let go of it, that UG change is going to change back into kinetic energy. So the same thing can happen with charged particles. Oh, right, okay, charged particles. I got 2 electrons. If I push them together, I'm storing OOE, because they don't want to be near each other. But I got to do work to push them together, okay? But if it's an electron and a proton, if I want to store energy, I'm going to push them apart. So that's where it gets weird in terms of how do you handle like charges versus how you handle unlike charges. But here's the beauty of this. The same great conservation law applies. You still have to conserve energy. Your OOE plus your kinetic energy still has to add up to a constant. So, you talk about electric fields. Oh, okay, cool. So, I've got a negatively charged plate and I have a positively charged plate, just like in a battery. So, quick refresher. Thatch, if I have a negatively charged plate on the top and a positively charged plate on the bottom, what's the direction of my electric field? Up or down? Why?
Because if you put a positive test charge, it's going to move up.
Okay, remember electric fields are determined based upon the direction a positive test charge moves. Okay? So if I put a positive charge in here, what's it going to do? Why is it going to go up? There's 2 reasons. Sydney, what's one of them?
It's being repelled by the positive plate.
Right, it doesn't like being near the other positively charged plate, so it goes, hey, deuces, we're out. So not only is it repulsed here, what's it also being doing? Attracted. So that's like, imagine you're at a party and you're standing, God forbid, by a group of freshmen to which you were repulsed, okay, as well you should be. And on the other side of the room, there is a group of really cool physics seniors going, oh, come on, dude, okay? So you're going to migrate that direction for 2 reasons. You're repulsed by the freshmen, and you're attracted to the really cool physics seniors on the other side of the room. Okay, it's my story, go with it. Don't sit there and go, they're not cool. Yes, they are. Okay? Now, let's say this is Gap-Shawn, okay? And Gap-Shawn is over here with the really cool physics kids, and there's a group of freshmen over here. What am I going to have to do to get Gap-Shawn over by the freshmen? I got to do work, right? Why, Gap-Shawn? Why do I have to do work to get you over there?
Because I hate freshmen.
Yeah, you don't want to go in that direction. It's like, come on, Gap-Shawn, work him, I don't want to go, I don't care. It's a story, work with me, okay? Now, again, as soon as I let go of it, what's going to happen? As soon as I let go of Gap-Shawn,
He's going to go backwards you.
he's going to go back to the cool seniors. Now, what if it's a nerdy freshman?
It's going to move away from the physics students.
It's going to move away from the physics students because you all are going to repulse him. It's like, get away, go away. And he's gonna feel more comfortable with the other nerdy axe smelling freshman. Okay? Oh, it's true. Don't act like that's
No,
not true.
it's lucky if they smell like axe.
Okay, I'm giving them the benefit of the doubt. Okay? So, this is why you can't say, oh, work is always going towards the positive plate, or work is always going towards the negative plate. It depends upon what that charge is. So, if this is the positively charged plate, okay, and you let go of, and you have a positively charged particle down here. So you got negatively charged up here, and you got a positive charge down here. As soon as you let go of it, what's going to happen to the amount of kinetic energy? It's going to increase because it's going to be going faster and faster and faster. If I shoot Gap Sean out of a cannon towards the freshman, as Gap Sean is going towards the freshman, what's going to happen to the velocity of Gap Sean? It's going to decrease. So again, when you look at whether something's going to speed up or slow down, you have to look at the direction of that particle relative to that field and whether that's a positive or negatively charged particle. Okay, I am done.
My wishes come true.
Well, don't get so excited about that. Yeah, it's not bad.
I just wanted to be silent. I don't care how difficult it is. I'm getting bored. You know how dangerous it
Yeah, you see someone using like, oh, okay. I guess I'll go back and see.
Guys, I'm just gonna look at the recordings during
You know how dangerous it
There you go. That's it. I told you it wasn't bad. And you're that's all.
How many
I'm gonna be
parts
honest,
each?
don't know what I got.
26 parts in the first
There's really not. I mean, like, this is what it took me. Okay? So, it's not cool. Now, since you're technically my TA, if you can do the assignments, they're going great. I mean,
I figured I'd just like do them last, probably, like I do my AV Chem first and then my AP.
yeah.
I'm just gonna make throwing this guy.
I mean, I'm not gonna rate it, but this will play out.
This will help me.
When you do, because you're gonna, vicariously gonna pick up some other physics.
Bless you.
Some other physics. Because it's concepts like kinetic energy and potential energy. So you're gonna do vicariously more of a lot of physics. By being.
Are we assuming it's one?
That's the excuse I make.
On problems? Yes.
Down by itself.
1 through 4. If you really want me to make that clear, 1, 2, 3, 4. Does that help?
How could
The only person who know that is Jack John.
It's not.
No. Some other people screwed it up too.
That's not.
It wasn't just Gap Sean.
Like,
I think they were all from May South. Now, that was AP Chemistry.
Yeah, I was 18.
Yeah.
I think it's